So the next thing to build into our mathematical model is the idea of gravity and gravitational forces, and we're all familiar with the basic idea of how gravity works. I've got a pen or something, and I drop it and it falls. You know? Same principle applies to other objects. I've got an interesting die here where all the sides are 6, and if I drop it, it falls. And the basic idea is that whatever object we've got, whatever particle it is that's falling towards the ground, if it's in free fall, then it's going to be accelerating downwards with an acceleration of g meters per second squared, and g is equal to approximately 9.8 if we're on the surface of the Earth. But we know that the equation Fr equals ma now is true as well. This is Newton's second law. So if this has a mass of m kilograms, then actually the force that's pulling this down due to gravity must be equal to m times g, because then we'll have the resultant force here, mg, is equal to m times a, and here a, the acceleration, is g. So standard situation here, we've got an object in free fall, and we model this force here of m times g downwards on it. I notice here this is a very simple model, so for example we haven't included anything like air resistance in here, so really actually it might not be accelerating downwards with g meters per second squared. It might be a bit less like that if I add on another force above it to have some air resistance. But that's the basic situation. And the other thing we know about gravity, of course, is that here at some point I drop the pen and it stops. And gravity is still having an effect on the pen at the moment, but it stops because the desk that it's fallen on has got in the. And so if we have a particle just sitting on the ground here, then we've still got that force due to gravity acting on it. Let's say it's still got a mass of m kilograms, so it's still got a force of mg newtons acting down on it here, but it's not moving. So we know here that in this particular situation, the pen is just on the table, the resultant force on it is going to have to be 0. So we've got another force coming up on it, also equal to mg, which is what we think of as the contact force, sometimes also called a normal contact force, not because it's common or ordinary or anything, but actually because it's perpendicular to the object it's in contact with. So normal in math is another word for perpendicular or at right angles or 90 degrees, and this force here is normal to the level of the ground. And this gives us then that the resultant force in this particular situation is 0. But the contact force doesn't always have to equal mg. For example, I've got this bag of marbles here now, and when I apply a small force upwards, I'm actually pulling up on the bag of marbles slightly at the moment, but nothing is happening, it's not moving. And as I increase the amount of force, then eventually that bag of marbles comes off of the desk. But there's clearly possible situations in between enough force to lift it off the desk and 0 force, when I'm just applying a little bit of force. So if we draw this picture again here now with my so the particle I'm thinking of is my box of marbles. It's got whatever mass it's got, and it's always got that force downwards due to gravity of mg. But actually I'm also applying a bit of a force upwards, say let's call it F. Then if this bag is still at rest, the contact force is not just mg anymore, but it's mg minus F, because when I add these two forces together we get mg, and they cancel each other out. So for example, if this mass actually was something like 10 kilograms, then the force down here would be about 9.8 times 10, or 98 newtons, and if there was a force upwards on it of 40 newtons, say, then this contact force would only have to be 58 newtons to keep this balance. So got this idea that the contact force from the table or whatever else, the ground level, is just enough to counteract any downward resultant force that will get in the way. But of course, if the upward force were bigger than the weight, so I've just drawn it again down here, let's say the force upwards was 150 newtons, then that'll be enough to actually lift the object off of the ground, counteract the weight, and then we won't be in contact with the surface anymore, so there won't be any contact force at all. And there's also that sort of limiting case where the upward force is exactly the weight, where although they are technically still in contact, there's no actual contact force because I absorbed all of that into my force lifting it up.